This is one of the most dangerous children's toys ever made. Inside it are not just 3 low-level radiation sources. It even includes 4 bottles filled with uranium-238 ore. Who thought it was a good idea to turn this into a toy for kids? It was released in 1950 by the Gilbert Toy Company, the Uranium-238 Atomic Energy Lab Kit. It literally tried to teach physics starting from childhood, and there were many ways to play with it. The simplest was hide and seek. Have a friend hide one of the radioactive sources, then use the Geiger counter in the top right corner to find it. When the counter starts clicking faster and faster, it means you're getting closer to the radiation source. What shocked me even more was that this toy even included a Nobel Prize-winning invention, the Wilson cloud chamber in the center. With just a simple assembly, kids could use it to watch radiation particles draw beautiful and strange trails. It was invented by British physicist Charles Wilson. So how does this device make those rays visible? Let's build a cloud chamber and take a look. Place some dry ice on a tray. Cover it with a clear container that has a baffle inside. Secure it, then pour a small amount of alcohol from the top. Next, drop a small piece of radioactive material into the chamber. Soon the chamber fills with alcohol vapor. As the dry ice sublimates, the temperature inside the chamber drops. The alcohol vapor becomes supersaturated. This state is similar to supercooled water, like when you slam a bottle on the table, and the water instantly freezes into ice. So when radiation particles enter the chamber, they collide with the gas molecules inside, ionizing them, producing free electrons and ions. The supersaturated alcohol vapor condenses on these ions to form tiny droplets. And that's what creates the streaks we see, white trails like airplane contrails. So here's the question: how can we tell which type of radiation created each of these different tracks? Different radiation particles produce different patterns. Alpha particles are heavy with strong ionizing power, but they lose energy quickly, so their tracks look thick, short, and straight. Beta particles are light with weak ionizing power, so their tracks are long, thin, and curved. Gamma rays carry no charge, but when they collide with electrons, they can leave broken zigzag traces without a clear starting point. Finally, back to this toy set. Was it actually dangerous? Even though the Gilbert Company claimed it was safe, and included a 60-page instruction booklet, it was still, after all, a children's toy. For kids with no training, if they accidentally broke one of the glass vials of uranium ore, inhaling it could cause severe internal radiation damage, and the nuclear contamination would be irreversible. So it was forced off the market just 1 year after its release. Can you believe it? If this clock had been running since the extinction of the dinosaurs, its error today would still be less than 3 seconds. What kind of clock could possibly have such insane precision? Its core material is this liquid in front of us that looks like gold. It is also the metal with the strongest contrast in appearance. At room temperature and pressure, it's as soft as modeling clay. You can cut it apart with a gentle poke. Hold it in your hand for a bit and it melts. After cooling for a while, it forms pure crystals like gold leaf. Although it looks very beautiful, its reactivity is frightening even to sodium and potassium. It starts smoking the moment it meets air, and if ignored for a bit, it self-ignites. Throw it into water and it explodes instantly. How can a metal as volatile as cesium keep time so precisely? This comes from the restless electrons in the outer shell of cesium atoms. As they orbit the nucleus, they reside in different energy states. Their orbital paths differ as well. These orbitals are called energy levels. Electrons in low energy levels absorb electromagnetic waves and jump to higher levels. Conversely, when electrons fall from high to low levels, they emit electromagnetic waves. And this electromagnetic wave frequency equals the energy difference divided by Planck's constant. In other words, the electromagnetic wave frequency of transitions between the same atomic energy levels is fixed. It is exactly this property of cesium atoms that allows the radiation emitted during electron transitions to calibrate an electronic oscillator, thus achieving precise timekeeping. Therefore, in 1967 the International Committee redefined 1 second as the duration in which the ground state of the cesium-133 atom undergoes 9,192,631,770 transitions between 2 hyperfine energy levels, and cesium atomic clocks have an accuracy of differing by only 1 second in tens of millions of years. However, this raises a question for me. Isn't it enough for clocks to just keep time? Why pursue such extreme precision? We know that the Earth's rotation of one cycle is defined as 24 hours. Dividing this time by 86,400 gives the length of 1 second. But because Earth's rotation speed varies, the second defined this way is not stable. Until the appearance of quartz clocks in 1972, which greatly improved clock accuracy, they used the property that quartz crystals vibrate mechanically at a regular rate when electrified. Electronic circuits convert these vibrations into precise time signals to keep time. However, limited by the quality of quartz crystals, the resulting time was still not accurate enough. The quartz clock used by the Greenwich Observatory in the UK still had a daily error of 1 millisecond. This value seems tiny, but it is far from enough for applications requiring extreme precision, such as satellite navigation that we use every day. It sends signals to Earth via electromagnetic waves, and electromagnetic waves travel at the speed of light, which is about 300,000 kilometers per second. Even if the satellite signal is received with just a 1 millisecond difference, the positioning distance would be off by 300 kilometers. Would you dare to use such navigation? Therefore, today's GPS satellites all rely on atomic clocks for timing.